Yes, thanks, Ender, and thanks everyone for coming. So today I want to introduce to you an interesting type of chimera that likes to play on a seesaw. But before I do that, since a lot of other talks in this session are also going to talk about chimeras, so let me just try to describe chimeras in general for the next few minutes. So when an average person hears chimeras, they mostly think of this hybrid monster from the Greek mythology. But of course, for us who study collective dynamics, there is another meaning for chimeras. Sometimes a fully symmetric system will undergo a symmetry breaking process and ends up with part of the system highly synchronized and part of the system behaving incoherently. Such states with coexistence of coherence and incoherence were first discovered 2 decades ago and were named chimera states because of the hybrid nature of the dynamics. Since then, chimeras have been found in a wide range of systems, from chemical reaction systems all the way to laser arrays, and they can arise from both phase oscillators and chaotic oscillators. One example of chimera dynamics in nature comes from dolphins. So dolphins, they do not sleep in a naive way like we do. They only have half of their brain asleep at a time, while the other half stays awake. This allows dolphins to keep swimming and stay alert while sleeping. In terms of neuronal dynamics, the sleeping half of the brain is highly synchronized, and the non-sleeping half is very incoherent. More interestingly, the sleeping and non-sleeping halves of the brain switch roles every 10 to 20 minutes, so both sides of the brain can get rested. You can imagine this as 2 chimeras sitting on the 2 ends of a seesaw, which can occasionally switch between 2 stable states. As one chimera goes up, the other goes down, and vice versa. So people often want to know how often does the system transition from one metastable state to the other. A double well potential is a picture most of us would think of when we talk about transitions between metastable states. It governs all kinds of dynamical processes, from spin flipping to protein folding to chemical reactions. Traditional theories predict that as the level of noise decreases, the waiting time between switching events increases exponentially, meaning someone could be stuck on the ground or in the air for a long time when noise is small. But is that really the case? Or is that always the case? Here, we look at a 2-cluster network of chaotic oscillators. Each node is coupled to its neighbors in the same cluster and also interacts with nodes in the other cluster. The node dynamics do not matter too much. Here, for simplicity, we use logistic maps. Now, let's introduce a tiny bit of noise with intensity around 10 to the minus 10 and simulate this system starting from random initial conditions. The upper and lower panel show the state of each node in the corresponding cluster. We give each oscillator a unique color, so the stretch of trajectory with only a single color means the oscillators in the corresponding cluster is synchronized. The middle panel shows the synchronization arrow in both clusters. The orange curve corresponds to the lower cluster, and the blue curve corresponds to the upper cluster. You can see a chimera quickly emerges from the random initial condition, where the upper cluster is incoherent and the lower cluster is synchronized. This goes on for a while. Then, at t around 1500, without any warning, the lower cluster becomes incoherent and the upper cluster becomes synchronized. This back and forth switching behavior persists for all time t. What is puzzling here is that when we do stability analysis, each chimera is actually linearly stable in the sense that it has negative transverse Lyapunov exponents. Yet, as we have seen, extremely small noise can cause frequent transitions between the two. In order to better understand this crazy dynamics, let's look at it more systematically. This log-log plot shows the relation between the average switching period and the noise intensity. You can see perfect power law dependencies between the two, which is in stark contrast with the exponential scaling in typical stochastic transitions. What this means is that the chimeras here are extremely sensitive to noise because the transition rate decreases much slower with noise intensity in a power law scaling than in an exponential scaling. As a consequence, we observe frequent switching events even at the resolution limit of computers using double precision floating point format, which is around 10 to the minus 15. So, even if I do not introduce any noise in my simulations, the round of arrows of my computer would already induce frequent switching between the two chimeras, despite them both being linearly stable. In fact, such switching can be triggered by arbitrarily small noise, as long as the noise intensity is not exactly zero. So in our seesaw analogy, even a light breeze can potentially cause a seesaw to swing up and down erratically. So what is causing this anomalous scaling behavior? An intuitive explanation is the following. Because the dynamics of the chimera states are chaotic, the minimum transition barrier separating the two chimeras changes over time. Here, you can see it is a wild landscape with ever deeper valleys. That is, you can find a transition path that costs arbitrarily small energy if you wait long enough and introduce perturbations at the right time. This plot basically shows the distribution of barriers with different heights. And it should be no surprise now that this distribution is answer power law. If we compared those exponents here with the exponents from the previous plot on transition rate, you can see that they match with each other perfectly. So in a sense, the power law switching behavior is being dictated by the structure of the time-dependent transition barrier. Here is another perspective. If we ignore noise, we can map out the basin of attraction of the two chimeras. Here we show a two-dimensional section of the initial condition space. So if an initial condition gets attracted to one chimera, we color the point orange. If it converges to the other chimera, we color the point blue. You can see a clear fractal structure in those plots. And no matter how much we zoom in, the two colors are always intermingled together. For any orange dot, you can always find a blue one arbitrarily close to it, and vice versa. This structure is called intermingled basins, which is a special case of riddled basins. The two ingredients for riddled basins are symmetry and chaos, which are also what gives rise to switching chimeras. So one interesting symmetry here is the reflection symmetry along the diagonal line. So any orange dots on this side of the plot, when mapped to the other side, would become blue, and vice versa. And this stems from the symmetry between the two clusters. It is worth noting that the chimeras are the only two attractors in the system. So the switching chimera state is robust and fragile to noise at the same time. They're robust in the sense that chimeras attract almost all initial conditions, and fragile in the sense that arbitrarily small noise will trigger the transitions between the two chimeras. I shall mention that this is different from heterokinetic switching, which is between saddles instead of attractors. And thus, heterokinetic switching would persist even without any noise. Whereas here, we need some noise, despite the noise can be arbitrarily small. So here is a different section of the state space that directly connecting the two chimeras. One chimera corresponds to the top boundary, and the other chimera attractor lies on the bottom boundary. If one starts closer to one of the chimera attractors, then it is more likely for it to converge to that chimera. The probability of escaping to the other chimera approaches zero algebraically as the distance to the attractor decreases, but it remains positive for any finite distance. This can be seen from the blue speckles penetrating arbitrarily close to the orange boundary and vice versa. So linear stability, it only considers infinitesimal perturbations. And that's why switching can happen for arbitrarily small noise, even though the two chimeras are both linearly stable. If you are interested in learning more about Riddled basins, including how measure theory comes into play, I recommend this classic from Zhang and others more than 2 decades ago. So with all this talking of infinitesimal and arbitrarily small, you might be wondering, how relevant is switching chimera in the real world? To answer this question, I collaborated with Joe and Raj from the University of Maryland, and they built this optoelectronic oscillator network, which involves a lot of fun stuff like lasers, FPGA, etc. So here, each node can be modeled as a discrete map with sine square mapping function. We first performed simulations to map out the parameter region where switching chimeras are expected. Then we focused on 2 representative sets of parameters and used them in our experiments. By varying noise in the experiments, we observed the same power law scaling between the switching rate and the noise intensity. So switching chimera is not a fragile thing. It can be consistently observed in experiments under realistic conditions. And here is an animation of the experimental time series. You can see that at any given time, one cluster is synchronized and the other cluster is incoherent with intermittent switching between the two. You can see the same from this spatial temporal plot as well. So one interesting next step is to look for switching chimeras in nature. But where shall we look? Here's a clue. For certain songbirds, when they sing, their brain activity will switch between the left hemisphere and the right hemisphere. What is interesting is that this switching is highly irregular, which is shown in the middle of this plot. Such irregular switching is not easy to explain by hypothesizing the existence of a certain, by assuming there is a central pattern generator, which would normally give rise to regular periodic switching. On the other hand, the lack of a fixed switching period fits the dynamics of switching chimeras perfectly. Thus, switching chimeras could potentially provide a mechanism for this irregular interhemispheric switching of brain activity. A promising next step is to look for switching chimeras in more realistic models of brain networks, and also to test whether the same power law scaling can be observed from real brain data. Let me just finish by thanking my collaborators and replacing these monstrous chimeras with something more likable. And I'm happy to take any questions.
Thank you very much, Yuanzhao. Are there any questions? I can't see any questions in the Q&A section. Yes, there is one by Sergei Yanchuk. Can one say that the chaotic attractor Chimera contains a set of a zero measure, that is a periodic solution embedded in the attractor that is transversely unstable? If I correctly remember, this is the case for the classical Riddled basin.
Yes, exactly. So yeah, that's basically the conditions for Riddled basins. So to make it a little bit more technical, the Riddled basins are characterized by being transversely unstable when you calculate your transverse Lyapunov exponents using the natural measure of the attractor. And what you just said was basically saying, so sorry, the previous one should be transversely stable. And what you just said is that the attractor is transversely unstable and have a positive Lyapunov exponents when you use a different measure, which concentrates on this periodic orbit inside the attractor.
Okay, thank you very much. I see another question by Sanjukta Krishna Gopal. Hello, Sanjukta, nice to see you. The question is, do you observe regions in parameter space where only one chimera becomes unstable?
Right. Okay, so this is not possible because if you look at the network we are considering here, the two clusters are perfectly identical. So by the symmetry argument, each cluster would have the same stability. And that's actually one reason why Chimera is interesting as a symmetry breaking phenomenon, because you normally wouldn't expect the two clusters to show different dynamics, but due to symmetry breaking, one cluster would be synchronized and the other cluster would be desynchronized.
Maybe I could jump in and extend that question, because we have done some simulations on this unihemispheric sleep associated with chimera on one side or on the other hemisphere of the brain with using empirical data. So we have used empirical diffusion tensor MRI data, and in fact from these data there is a slight asymmetry, a slight structural asymmetry in the two hemispheres. Still, in spite of that slight asymmetries, we have been running the Fitsunagumo model and observed this switching between two symmetry breaking states. Either one, in that case, one hemisphere was more synchronized than the other, and they switched well, not periodically, but randomly. And this is in spite of this slight structural asymmetry. In fact, for other parameters, we even observed complete synchrony in one hemisphere and asymmetry in the other, so a real chimera state. But my question would be, have you tried to make the parameters slightly different, not very much, but slightly different? And do you find some robustness of this switching behavior?
Yeah. So what you just described are very interesting. And yes, we did run simulations by introducing, parameter mismatch among those nodes, and also by adding noise, as we have already done, and answering the experiments as well. So when we study the effect of parameter mismatches, what we found is that they have a similar effect as noise.
Mm-hmm.
So basically, when you have this heterogeneity or the parameter mismatch at a level, say 10 to the minus 10, then you would have a similar effect as if compared with when you have identical oscillators and have a noise intensity of 10 to the minus 10. So when you have parameter mismatch, even without a noise, you will see this switching between the two.
So very, very small noise and a slight parameter asymmetries. That's what you have been mentioning. Interesting, and it agrees with our observations in empirical brain structural simulations that we still have this switching of the two symmetry breaking states, and it seems to be a very important feature in biological systems in the brain, of course. So it's very interesting.
Yeah, it's definitely a robust phenomenon for sure.
Yes, robust, that's what you mentioned. It's delicate, fragile, but still robust in some sense.
Yeah.
Now I see one question by John. Will you consider the photoelectronic experiment as a regular chimera switching?
Sorry, I probably need some clarification
Yes.
on the
so
question.
Maybe I read again. Will you consider the photoelectronic experiment? This is the experiment by Raj Roy and Joe Hart. Will you consider that as a regular chimera switching?
All right. So okay. So we are talking about the experiment showing here.
Yeah.
Yes.
It doesn't look regular. I mean, for me, it doesn't look regular. It looks like random switching according to some maybe power you found.
So this is basically the same switching camera as I showed for the numerical system, and the switching is not periodic. There is not a there's not a fixed period that the two clusters switching between each other, and actually we plotted the distribution of the switching periods, which actually follows an exponential distribution, which suggests that the switching is actually a Poisson process without any memory, meaning when the previous switching happens, that has zero effect on when where the next switching happen.
Okay.
I hope this answers the question.
I think so. So at the moment we have no more questions, but also the time is running. So thank you again very much, Yuanzhao. And